All right. So in a high-level language, when we create we're talking about language like C. So this is a high-level, strongly typed language. I'm almost positive the book isn't taking types into consideration because basically I think up to this point we're just assuming that we have a CPU that only knows how to deal with numbers, and we have a language that only knows how to deal with numbers. So the type is kind of insignificant. We would have to get a lot fancier if we want to start supporting. We would say we need to get a lot fancier if we want to support other types, but the reality is that ints are numeric, chars are numeric, strings are numeric. Strings are collections of chars. And you use a pointer to get to the beginning of that collection. There's collections of chars stored in contiguous memory. And I'm guessing the book probably talks about arrays in this section, do they?
I think when we're talking about the offset, it's
Yeah.
use the array.
Yeah. All right, so variables in general. So if we think about a variable in C, we'd say like int I, capitalization. It's going to be the end of me. All right, int I, we're just going to let it capitalize, and that's just the way it's going to be. And then we say I is equal to 5, something like that. So to define a variable in C, we have lines of code, and these guys happen to have semicolons between the lines, distinguishing, separating the lines, something like that. All right, so we need a program that's going to be able to read in some code, read in from a file, some code. So we're going to do some file I/O in Java, and actually file I/O in Eclipse sucks a little, just because of the way Eclipse makes their projects. But that's okay. We could just choose not to use Eclipse.
Why we have to use it?
At this rate, we should use Android Studio.
That's the same.
Oh my god.
Huh?
No. Let's make an interface.
Well, I'll just use Atom or something.
Oh
yes, let's do Atom. Let's do Atom.
I work with
You want to do Atom?
every single day. I'm fine with Atom. I have it up already.
Okay. The value of me showing you an Android in an Eclipse rather is that you can see how to do file I/O in Eclipse if it's ever of interest to you. Is that of interest to anybody? You want to just do an Atom?
What is file?
It would be reading in from a file. So if I have a file called like mycode.txt or mycode.c, and I had my Java program read that in, you can do that very trivially if you have your Java program sitting in the same directory as your C file. But because of the way Eclipse handles their packages, where they create the separate files, we have like a source folder and a bin folder and stuff like that. It makes it very difficult, not difficult, quirky to have a file that you then can do things with.
So you're saying it's easier in Eclipse or harder?
Well, it's the same code. You just have to go through a couple of headaches to figure out how to tell Eclipse exactly where your code lives. So if
you're suggesting Eclipse.
Well, Eclipse has, let's call Eclipse the better editor, but Eclipse is going to have that additional headache. But if it's of interest to you, we can do it. So if you're writing this at home in Java, Eclipse might be the tool you choose to use because it does all the command completion stuff and things like that for you, where Atom won't do that. So let's do it in Eclipse. So I'm going to do File, New, Java Project, and we're going to call this guy MIPS Compiler. And who knows? Maybe we'll find out that it's not as bad as it used to be. All right, so in my source folder, I'll write, Yes. So I'm going to create a new class. I'm going to call this guy, I'm just going to call it driver.java. All right, and then I'm going to go ahead and just do my public static void main. And we'll just do our little hello world program. And hit play, make sure this guy is a functioning program, and it is. All right, so now we want to be able to edit this. So I'm going to right click on my default package. I'm going to say new. And can I give myself I want to create a file. Create another kind of file. And let's general file. Actually, let me go back real quick. Untitled text file. Let's just go with that. All right, and then can I save it? Or is it just called untitled now? Where did that guy go? I'm going to say show in System Explorer. So where did it put the file? Because that's driver.class. Here's source. Oh, it didn't even attach it to my project. Oh, that's nice. All right, so I'll just close that. I'm going to say new, other, file, next, and we're going to call this guy test.c. All right, so this is detecting the C file thing and thinking I want to use Xcode.
You're creating a C file, I heard.
I right-clicked on source. I said new. I said other. And then under general, I chose file. And then I just named the file test.c. So it looks like a real C program. But it's just a text file. All right, and let me see where it ended up putting that. Did it put it in source? Okay, it did. It put it in source, which I think that's where the problem runs into. So it's technically in my folder called source. But when I compile, when I hit that play button in Eclipse and it compiles the driver.java, what it ends up doing is it puts the class file inside of this bin directory. So it's actually running it from this bin directory. So when I try to load that file, it's going to look for it in the directory with the class file. But it's actually in the directory with my source code file. So because Eclipse makes these things, it puts it in different places. So because they're trying to make our life look organized, they actually make file I/O more difficult. So what I'm going to do is I'll just go into here and we'll say Eclipse file I/O directory. I think this will probably just give us, relative paths in. Oh, he indicates that that should work now. That might be nice if we can make that work. All right, so I'm going to create a scanner input. Oh, Ninja. Still trying to open up Xcode. This guy's going to be a new scanner. And I'm going to build this guy out of a new file. And this is going to be test.c. And we have to import java.util.scanner. So while input dot has next system.out.println input dot next line. Oh, I don't want to open it in that. I want to open it. I want to open that in the clip. Whatever. I'll just open it in this. So we're going to say int I colon, and then I is equal to 7. And I wrote my simple C program there. 2 lines of code inside of a file called test.c. You can do that in Atom if you want, whatever. All right, so now the hope is, oh, I think it will open in here now. Nope. Whatever.
That's where you have to put in I.
Yeah, so the hope, I need to import java.io file. And this guy can throw an exception. Let me just do throws exception for right now, just to get this working before I explain what all this is doing. So I'm going to try to create a scanner which allows me to read stuff in from some input stream. The input stream, I'm going to build this scanner in terms of a file, and I'm hopefully going to be able to give it a relative path and say my file named test.c lives in the source folder. I actually think this isn't going to work because the working directory is actually going to be in the bin folder. So I actually kind of need to do //source/test.c, but maybe Eclipse does something funky here for us. So let's just see if this, oh, no, it worked. Reads it in for us. Life is good. All right, so that's actually an improvement for Eclipse. So what Eclipse said is we're going to make our working directory the base directory of your, let me go back to this. I'll just show source in System Explorer, and then I'll go up 1 level. All right, so here's my MIPS compiler that we're writing here. And inside of that is a bin folder and a source folder. My compiled Java code lives in the bin folder. My source code lives, oh, that's how they're doing it. They duplicate it in both folders.
That's easy.
Yeah. So what they're doing here is, oh, that's interesting actually that they're doing that.
The Java code goes in the bin file, and then the C.
Yeah, the class file. This is the compiled Java program goes here. And the source file is what we're editing. This is our Java file. And we actually put our test.c inside the source folder. We created it here. And what Eclipse is doing is it's managing it by keeping whatever we put inside of here equal to it.
Duplicated.
Yeah, it just.
Wait, what is the difference between the Java program and the Java file?
The Java file is the Java syntax. The .class file is the compiled Java syntax, which is equivalent to what we're doing. It's the MIPS code. The .class file is what happens when you run a Java program through the Java compiler. See, this is the problem with learning programming with a play button. So let me show you what ends up happening here. So if we go out to the terminal here, where's the directory for this guy? I'm gonna just go to show in System Explorer, open up my terminal. I'll say cd space, and I'm just going to drag the source folder in there. That gives me the full path to where it is. All right, so right now I'm sitting inside of my source folder for my Eclipse workspace MIPS compiler source. Now, this is what happens. This is what Eclipse does for us. You know that nice little play button up here that we just love to hit and say, oh, my program just magically works when I hit the play button. What's actually happening is it is compiling this .java file, and it is putting that Java file inside of a directory called bin. And the compiled version is called driver.class. That is Java bytecode. What is Java bytecode? That is the low-level language that runs on the Java virtual machine, the CPU that is called the Java virtual machine. This is not dissimilar to the compiler we're writing here that's going to convert C code into MIPS assembly, low-level code that runs on the MIPS processor. So if I'm here in the source folder and I run this through the Java compiler is called javac, and the name of my file is driver.java. Javac is the Java compiler that knows how to turn Java syntax into Java bytecode. This is an already written program that solves the problem that we're trying to solve in class. This converts Java syntax into Java bytecode. We're trying to convert C syntax into MIPS code. That makes sense? But this Java compiler already exists. If I run this, it'll compile my program, but see, it will put that .class file right here in that same directory. So now I can run that program by just saying Java space driver.
Did you make a class and the object? How do you call that? Did you make both of those?
No. If I removed, well, just remove star.class. Now I just have my driver.java. That's all that's in that directory. Driver.java and test C. But now if I run the compiler again, I have a new file that was just generated. That is the output of the compiler. That is our MIPS code. This just happens to be code that runs on the Java virtual machine. So what I'm saying is that when you hit the play button up here in Eclipse, what's actually happening is they are running that line, javac space driver.java. Then they're moving driver.class to /bin/ so that it's no longer in here, but it's actually in there. So that when you hit the play button, it then goes and runs that. So play button compiles it in source, moves the class file to bin for binary, then actually executes it by saying Java driver.
Is that what we wanted to happen?
It's an error because of the input stream for where the file lives. We have our code written in terms of the source/test. It's not finding a source/test here. If we were running it from the command line. Yeah, this is what we had to make Eclipse happy. Because Eclipse is running it from within the source directory. We could probably actually pull this off if we come up here and I do Java bin/driver. Oh, I said, oh no. Oh, it doesn't like me running it from outside the directory. Yeah. So if I wanted to make this run from the command line, I would take this off.
Because on the folder you have the text.
Yeah. So then I would go into source, I'd compile it, then I'd move driver.class to bin, then I'd go up to bin, and now I can do Java space driver, and it gives me my output.
Well, I think if we move the text.c makes sense because eventually it's running for the bin. So if you publish the project, you are not publishing the source.
Correct.
You're publishing the bin.
Correct.
It has to.
But this used to be a problem, but you're still having to run it in terms of your giving it a relative path. So right now, the code I have looks like this.
Yeah.
But if I run this code from within here, can't find the file.
It will.
Because I have to tell it the file is actually located in source. I actually suspect I could say bin slash and have it also work. Yeah. Because Eclipse is mimicking it in both places. Eclipse is saying, hey, look, you changed the file. I'll just make sure both sides, it's in source and bin. They both have that file for you. Well, it's what I'm showing here is all the management that Eclipse already does for us. But the point is that we want to really appreciate what this play button does. When you hit that play button, a whole lot more than just play is happening. That make sense?
My question kind of involved if we have the bin there,
Mm-hmm.
we can run it or we can do it through the command line, or no?
Oh, so if I write it like this?
Yeah.
No, it still won't because I run it from within the bin directory. So if I come here again, I'll compile it here. Then I'll move it into the bin directory. Then I'll jump up a level. I'll go into the bin directory, and if I do Java driver in here, still can't find it because it's looking for it inside of a directory called bin inside of here. And if I bounce up a level here and I say Java bin slash driver, it gives me an error because you can't load the, because of the package name. It packages in Java work as directory structures. So it thinks when I say run bin slash driver, it thinks I'm saying run the driver program that lives in the bin package. So bottom line is, if you want to use Eclipse, you do it the Eclipse way and let him manage your, yeah, it's got to be him. This is too convoluted of an organization system. All right. So we'll go back in here. You can choose source slash or test slash because Eclipse duplicates that file in both of those. Make sense? All right. So the code I have right here, what does this guy do? He reads in source code. All right. I'm actually going to move that into another class because we kind of want to have some objects for doing this. So we're going to have a class here. We're going to call this guy source reader. And then my source reader class, I'm going to have, we're going to say string file name. We'll say private string file name. And then we'll have our public constructor source reader. And this guy will take in a string file name. We'll say this dot file name is equal to file name. So we have that set up. Then I'm going to go ahead and steal our code from this driver thing up here, my scanner stuff. So we won't need these guys up here anymore. I'll go ahead and paste that code in here, except we're actually reading in. You know what? We can just pass it the whole file name. That way we can give it a full path. All right, then we're going to import java.util. Actually, we need to give it a try catch. So we're going to try to do this crap because a file not found exception can occur. And we will catch IO exception E, and we'll do like a system .err.println e dot, was it like, actually there's just an e dot print stack trace, I think. Yeah, there. So that'll show like an error message out to the system.error if something bad happens. But we fully expect to read in our file name, then we're going to try to read that file. So we have our scanner. We're going to read in this .file name. So long, and then I'm still just going to spit stuff out to prove that it's working, but we're going to do something else in there here in a second. And let's see here. No, we have Java IO file. All of them got imported up here. Okay. So we have our stuff. So now the idea here is that I should be able to come into driver, and I should be able to create a source reader. Source R is equal to a new source reader, and pass it the source slash test.c, and he should go and read that source slash, oh, it's test.c, not text. But that's what print stack trace looks like. With that red stuff, it just printed out there. But there's our actual stuff there. All right, so we just moved our code inside this object so we can do some stuff. Now, something we might want to do is we might want to have the ability to effectively have a collection of our lines of code, right? And then be able to work with them as individuals. Now, if we go back to the book here for a second, we kind of see where they're going with this. They're saying if we have an int x, let's just look at that very top one. So we differentiate lines of code in C with that semicolon. Semicolon says this is the end of one thing before the beginning of another thing, right? All right. So if we just have an int x, what are we doing? It's going to go and create a place in memory to store this. So let's start thinking about how languages work. Right? If I created an int x, a variable in Java and C, pick your high-level language, right? And I created an x and I set it equal to 7, which is ultimately what we're doing here. What am I doing? I am storing a 7 somewhere in memory. That's the purpose of variables. We go back to Lippmann Programming 101. How do people solve problems? We use memory, ask questions, repetition. Oh man, I thought that would fix that. Repetition. That would have been hilarious if it would have. All right, so memory, asking questions, repetition, and all of our programming languages, we implement memory through variables. We asking questions through conditionals, repetition through loops, and let's call it functions, procedures, however you want to say it. Now, just out of curiosity, and I promise I have not looked in the book, does the book talk about memory, if statements, and loops and functions in this chapter?
Yeah.
Yeah.
Interesting. Interesting. Remember at some point when I said something along the lines, this would have been years ago for some of you, that 100% of programming languages have facilities for these three things. And it just so happens that we're writing a compiler, we're looking to solve for mapping between the high-level version of defining a variable and the low-level version of defining a variable, the high-level version of an if statement and the low-level version of an if statement, because our MIPS processor already supports if statements, right? It supports subroutines. It supports loops. It's a fully functional processor written in Scheme. It's awesome that we didn't even use for our homework. Those are cowards. All right, so when we're sitting here, we think about human memory. We all know our name, right? Okay, we don't really recognize that we do it, but if somebody says, "Hey, what's your name?" you're gonna kind of do this little lookup. Yeah, there's a place up here, and you look it up and say, "My name's Mike, I think." Okay? Something's firing. Okay, right? And at some point, well, I mean, and this is why, you know, people who have, you know, memory loss and things like that, where they forget who they are, it's so debilitating. It's something we rely on as just a normal part of being a person, right? So we don't think about having to go look up a variable in our memory and ultimately resolve that variable to its value, and its value is Mike. We don't look for the variable named name inside of memory, ultimately get Mike out of it, and then report back, this is what I found. Give me a cookie, right? We don't do that. But we kind of recognize that is what's happening. Well, computers, programming languages, laying on top of a computer, a programming language empowers us to tell a computer what to do, right? So a programming language has facilities for mimicking all of these ways human beings solve problems. And one of those things is memory. Computers have memory. Human beings have memory. Human beings' memory is a pretty complicated thing. Computers' memory is a real simple thing. Big, long street, all the houses are on one street, right? So we have to have a way of saying, oh, you want to remember something. That's what we're doing here. Right here, I'm saying I want to build a place to remember something. Now, in C, we're naming that X. Now, why is that X important? Well, let me ask a different way. Is this X actually important in the assembly level side of things?
No.
How is it important on the C side? When I have X defined here, this X, every time I have an X inside the same scope, where for right now, and I'm presuming the way the book goes about it, we only have one scope, but it's possible with subroutines they get into secondary scopes. But in any case, assuming we only have one variable scope, when I define something named X, I'm actually talking about a memory location somewhere. But as a human being writing this high-level code, I don't care where he's going to put it. I don't care if that's memory location 5,000 or 8,000 or whatever. I don't care. Put it somewhere. Not my problem. I'm a high-level programmer. I'm using C because I don't want to deal with the whole memory mess, right? Well, it's kind of a bad reason not to use C, but it's better than working on the processor directly. All right, so I'm saying, look, I want to call it X because that's easier for a human being to remember. Really, I want to call it like my name or something like that. And I expect the computer to put that somewhere safe, but I don't care where. Because from that point forward, as a high-level programmer, I will always refer to it by its name, X. When I say X here, I mean this guy. I want you to go and find where you put him in memory. I'm not remembering that for you. You put him somewhere. But whenever I need him, I'm going to call him by the variable name I put out there. At the low-level side of things, we don't care about X. Unimportant. We think about things in terms of hardware registers and system memory. Super fast perform operations mathy stuff or long-term storage. What is MIPS called? Data memory? What do they call it? Or data file? Data file? No, they call it register file. They call it data memory. Okay, so if we look here at the mapping here, what happens? To create a variable named X, what we're doing is we are using one of our registers, T0, and we're loading the value 5,000 into it. All right, so with our picture, oh, I only had to read the screen to say it was registered. Well, actually, it is register file, isn't it?
Yeah.
So this is a bad picture. It's an ambiguous picture. Okay, but notice in data memory, what they've done is they've said, we have 5,000. That's where we're going to end up putting that 7 when we get to that point. But by me saying, I'm going to go ahead and move in, because effectively the super secret move we're doing right here is we are grabbing a chunk of memory and then putting a variable into it. putting a value into it. Are we allowed to have a variable that is occupying a place in memory but choose not to put a value in there? Yeah, we can do that. Could my entire C program just be int x semicolon? Sure. Pretty boring program. Good enough. Look, I'm just going to say, look, that's my spot. I'm not going to put nothing there. It's my spot. Make sense?
How is it representing now inside the assembly?
How do you represent null? Nothing. Usually default values for it will be 0, but you can't necessarily assume that. So the concept of null is not an assembly concept. The concept of null is represented with zeros or ones. So like we saw the less than thing. So usually we would say null as like a not true.
Okay.
Would be how we'd have to represent it in assembly.
Then
So the
how-
concept of nothingness only exists in high-level programs.
Then how it knows it is a real 0, but it's not
Yeah.
a
We don't.
default 0?
We don't. And when if you've taken programming classes with me, you've heard me mention before, never, ever, 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 ever assume that a variable has a default value. They always do, and it almost always is a 0. But if you want it to be a 0 or you want it to be a 7, put a 7 in there. Don't define a variable and then start using it as if you deserve that default value for some reason. Because what are we doing here? We're saying we're going to reserve your spot here in memory at 5,000. We're going to reserve that spot for you and pretend like the 7 isn't here yet because we're only in this first line of code here. Int x. We're saying, look, I found you a nice plot of land, memory address 5,000. That's your spot. But before you put anything there, maybe it's a 0 if nobody's ever used that spot before. Maybe it's 13. Maybe it's some previous guy's variable that's still stuck there because his program finished running. It's no longer reserved space, but his little 13 is still standing there. So if you don't initialize it to a value that you expect it to be, you're stuck with whatever is in there. Make sense? All right, so the corresponding line to a variable declaration is to pick an unused register, load into it the memory location of the next open spot in memory. So by this example here, they're jumping by 4, so we'll call this 32 bits, 4 bytes. So they're bite-sized chunks. So they have data memory divided up into 32-bit or 4-byte chunks. So this is memory location 5000, 5001, 5002, 5003. This can hold a value plus or minus 2 to the 31st power, negative 2.1 billion to positive 2.1 billion. Okay, but this very first line here says we're going to go ahead and reserve this bucket for your variable. And notice they put the little X next to it. Somebody's got to mark it off. Spot's taken. So that's my spot. If somebody else is going to come along with another variable, int y, maybe we'll give him spot 504, 5004. That can be his spot. The 5,000 is already taken and it's been marked off. Make sense? So we're going to have a way of marking off memory and saying this spot is taken. And we're going to have a way of releasing memory when a program is done so that we can possibly hand that out to somebody else. So we need to have somebody whose job it is to hand out spots, right? We're going to have a memory manager. In most high-level languages that you've worked with, Java, C#, who's the memory manager?
Garbage collector.
Garbage collector picks up old memory. Who creates new memory? Almost gave away the answer if you would have listened to what I said. Who creates new memory? New memory, new memory, new. The new keyword is our real estate agent.
Constructor.
Okay? The new keyword is our real estate agent. He's in charge of going out and getting us memory. He asks the operating system to go find us memory somewhere. Make sense? But that's the Java program's version of new. If I come in here and I say, here, I'm creating an instance of my source reader. And the source reader is going to have this, here's this new keyword. The new keyword says this is going to be a memory address, right? If I say system.out.println source R, the output of that is going to be crazy looking memory address. New keyword gives us memory addresses. That's what he does. Okay? So in Java, that guy goes and says, find me new memory. But if I say int I is equal to 7 like that, do we know that new memory does get created there? That we're going to be provided someplace in memory that we don't know about. I have no way of printing that in Java, but I'm going to be provided with someplace in memory where this 7 will live. And nobody else has access to that as long as I still have this variable in scope. As long as my program's still running and my variable is still usable, that's my spot. And somebody created that for me. Somebody got me that plot of land. They went to the operating system and said, look, we're looking for some memory for this guy. He wants to store 7. What do you got for me? Well, we got memory address 5004. Perfect. I'll let them know. That's what this is. This is the new keyword memory manager for a high-level language. We're effectively talking to the operating system and saying, I need a storage location to store in our dumbed-down version of C here. I need to store a number. In our world, we're just going to say all numbers are 32 bits. I'm guessing that's what the book does. Does the book go in talk about bytes and shorts and longs or anything like that? Or does it pretty much stick to just numbers? Hard ints for everything? All right. So the chapter is basically saying we are working with a version of C that only supports 32-bit numbers. It's good enough for us to understand how the architecture works, right? All right. So effectively, we're using very simple terms to talk to the operating system. We're saying, look, dude wants to store a 32-bit number. I need a place to put it. Tell me where I can put it. Guy says, no problem. This spot's already taken, but I can give you 5004. Cool. Go ahead and mark me down for that. So we'll get another little X there. That spot's taken. Make sense? All right, so we're going to need that guy who will hand out memory. We're going to need a memory manager. The guy who I could ask, I said, look, I need memory for a 32-bit number. Give me the first one that's available. Okay? So we're going to create a class here. We'll call this guy a memBucket. And my memBucket is going to have a private int value. Now we are limiting ourselves here where we're saying we're storing 32-bit numbers. So the fact that I'm saying a memBucket is 32 bits and its value will always be 32 bits. So that's what a memBucket is. Every house in our memory is 32 bits big. Okay? So private int value and then private Boolean in use. So we'll have a constructor for this, public memBucket. This guy will take in an int value as a parameter. We'll say this dot value is equal to value. We'll say this dot in use is now equal to true because he is in use. So when we actually put a value there, initially, it'll be in use. Okay? I'm going to give it another one just so we can mimic this. We're going to have a private int location. So this guy will take in an int. In fact, actually, the way I'm going to do this, he's not going to take in a value initially. This will make sense when I actually use it. All right, well, and we'll take a break in 2 minutes. Let me just get this first part. Mem bucket, we'll take an init location. We're gonna set value. We'll just put a value of 0 in there, the default value. But in use is false. This is an available spot for us. But we'll say this dot location is equal to whatever location was passed in. All right, but then we're gonna have a public Boolean is in use. And this guy will return this dot in use. So he'll return the value of whether or not this bucket is in use. That makes some sense? You're going to see how I'm going to use this in a second. I'm going to effectively build my memory. I'm going to build, let's call it from memory location 5,000 to 10,000 with a whole bunch of mem buckets. Each mem bucket I'll do steps by 4. So I'll do 5,000, 5004, 5008. Each one will have a location, 5,000, 5004, 5008, and none of them will be in use because the in use is initially false. So I'm going to establish my memory. That way I now have a little place to go and look and say, dude's asking for some memory to store something. Let me give you a mem bucket that's available for you, and I'll tell you what address that is. Okay? So let's take 5 minutes, come back at 9:05, and we'll keep chugging.